Okay, so today we're going to continue along with looking at odds ratios, and then also we're going to look at logistic regression when we add more variables. So we're going to look at multiple logistic regression. So first off, so last time we looked at the odds ratio, which we said was a multiplicative the multiplicative increase in the odds as x changes by one unit. But now with a binary predictor variable, 1 unit is going to be the difference in odds between when x is 0 and x is 1. When you have a binary predictor variable, you only have two possibilities. So for example, if it's gender, our odds ratio, if our binary predictor is gender getting into med school, like we're going to look at here, is it going to be different? Is the probability of getting into med school going to be different for males and females? So there's a very easy interpretation of the odds ratio when you just have a binary variable like gender. Okay? So let's look at that. And so this is the same example that we looked at before. And so we have these 55 students all applying to med school. And they were classified as either male or female. So we want to know, is gender related to acceptance? So we can use this simple logistic regression with this 0-1 binary predictor variable, gender. All right, so this is what the computer gave us as the logs odds equation. So what is this saying? This is saying, so these right here are our coefficients. You know, our betas are B0 and our B1. And so we have the predicted log odds of getting into med school. That predicted log odds is going to be negative 0.2231. That's our intercept. Plus, and then we have a slope in front of the gender right here. And so that's plus 0.8109. And that's in front of our gender variable. And we've coded that right here as 0 for males and 1 for females. So when we see this positive slope right here, it's saying that females have a better odds of getting in. They have a higher chance of getting in. Right here, it's not significant. We'll look at that later. Doesn't look like it's significant, but let's just see what it's saying here. Let's interpret this. So what's the odds equation? So the odds equation, we're just going to exponentiate both sides, anti-log both sides, and we get the odds is equal to e to the negative 0.2231 plus 0.8109 times our gender variable right there. So what's it going to be for males? Well, males are coded as 0 here for gender, so it's just going to be that. So the odds for males is just going to be e to the negative 0.2231. And that turns out to be 0.8. Okay, so what are the odds for females going to be? The odds for females are 1, so it's just going to be, the odds are going to be equal to that times e to the female slope. Another way, you could just see it as e to the negative 0.2231 plus gender is now 1. Okay? Which is the same thing as multiplying this times e to the 0.8109. All right, and so this, this is the same thing as e to the, this is just arithmetic, times e to the 0.8109. And that right there is the odds ratio for gender. The odds ratio for gender. And it's explained right here. It turns out to be 2.25. So if you multiply 0.8 times 2.5, you'll see you get 1.8. All right, so that's, oh, it also says what's the probability for males. All right, so this is the odds. Do you remember? So if we want to get the probability, what are we going to do? The probability is equal to what? The odds over 1 plus the odds. So it's going to be 0.1 over 1.8. And that's 44.44 repeating percent for males. So that's the probability of getting in for males. And for females, it's going to be, what will the probability be? So here you look at females, and the probability, this is the odds, and the probability is going to be 1.8 divided by 2.8. And that probability for females is 64 point, gosh, I can't remember. 0.29% rounded. So that's the difference there. Now, so if you compare the odds of females getting in to the odds of males getting in, well, that's our odds ratio. And the odds of females getting in is just this odds ratio, right here. There's the slope. I'm just looking right here. Here's the slope up here, right? And when you take the odds, that's going to be a multiplicative factor of e raised to that power. So it's e to the 0.8109 times higher. I'm just repeating myself here. The female odds is e to the 0.8109, and that's approximately equal to, rounded 2.25. All right? So basically all we're saying is what? That this is a special case of our previous definition of the odds ratio is the multiplicative change in the odds for a 1 unit increase in X. And here the 1 unit increase just means going from male to female, because we coded males as 0 and females as 1. If we coded them the opposite, it would be the same thing, except that the sign here would change. So instead of multiplying by 2.25, you'd be dividing by 2.25 as you went from. Just depends on what you code as 1 and 0. That's the multiplicative change. All right, so now let's move on. All right, so there's you probably are thinking, well, there's other ways we could do this problem, right? We could do this problem back in Stat 100. We could have done this problem as a chi-square test for independence, is whether you're male or female, independent of whether you get into accepted to medical school. Is knowing whether somebody's male or female, does that give you any information about their chances of getting accepted to medical school? We could have also done it as what? A two-sample z-test. Are the percentage of females getting in, is that different than the percentage of, the null hypothesis would be the chance of a female getting in, the percentage of females who get in would be equal to the percentage of males who get in. And is this difference we see of 66% versus 44% significant or not, or is that just due to the luck of the draw? And then we would just do a two-sample z-test. And depending on how you estimate the standard errors for these, they're basically all going to give you very similar results. And in the limit, if n is large, they'll give you almost identical results. So there's many different ways we can do this problem. It's a very, very simple problem. Notice that in all the ways that I described, the t-test and the f-test never came up. Why? Does anybody know? That you'll never be taught to do this type of test with a this type of example using a t-test, even if you have a very small sample size. It's because these are all basically based on the normal approximations are this to the binomial, right? So if you're predicting percentages, you basically have zeros and ones counts. And so you'd always be, if you wanted to do it exactly, you'd do a binomial. And then the norm, as your sample size gets large enough, you're taught that just use the normal approximation, right? Which is, basically use the normal curve. You're not going to keep using the binomial when you have a big sample size. And unfortunately, you're never taught that's exactly the same thing that should happen when you have means, quantitative-wise. At some point, you can say, hey, the t-curve, yeah, just use the normal approximation. But you don't. And the only reason you don't is because, at some point your f, if you have a large enough sample size, we learn here in Stat 200, yeah, you can approximate it with the chi-square distribution. But you'll never see that anywhere else. And it's only, unless you get into upper level math courses, stats courses. Sure, if you get into high enough level, you'll see that all the time, but not in the middle level, usually. Because why? It's only because you're being taught to the software. The software, it's hard to approximate. It's hard for computers to do the binomial, right? There's all these factorials that have to do, it would be hard. But it's very easy to program a computer to keep doing the t-distribution. No matter, there's an analytics solution, it's very, very easy. So that's why. It's because the computers don't switch over, so you don't switch over. But pedagogically, it's much, 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 much easier to think of in terms of chi-squared and z, and everywhere but regression, that's what you'll be doing. If you do anything else but regression, you'll be doing that, but it's just an artifact of having these computers easily not switch to the normal approximations. So that's the idea. Okay, so now let's look at this. So this is the chi-square test. We could do a chi-square test for independence. And now let's look at the odds. We could even just looking, why don't we just look right here at these four numbers here, and we can get the odds. Okay. So the idea is we could do the same problem by a chi-square test for independence, and notice how we get almost the same chi-square statistic, not quite. We'll talk about that later and why not when we do inference next time. But let's look at our odds here. So if we want to compute the odds for females, what can we do? We can compute it. Will we get the same thing as we got here? Here we got 1.8 for females and 0.8 for males. Let's just do it quickly, just looking at this 2x2 table. All right, so the odds for females, what would it be? Just looking here. So your odds for females would be what? Now, odds are success over failure. So you can think of it as 18 over 10. Or you could think of it as p over 1 minus p. So p over 1 minus p would be what? The probability of getting in would be 18 over 28, right? 18 over 28, divided by the probability of not getting in, 10 over 28. But it's 18 over 10. It's yes to no ratio, success to failure. So this is a simple problem. You can do lots of different ways. So here, for men, what would it be? Well, the odds would equal what? 12 to 15, or 12 over 27 to 15 over 27. So we get the same thing. And the odds ratio is going to be the same. The odds ratio is going to be 1.8 over 0.8. the odds of females over the odds of males, because females are coded as 1. So that's 2.25. Okay. And how does it compare? Same. To within rounding error. Okay, and you have homework that's pretty much exactly like that, your first homework problem that is posted now. Okay, so now let's look at multiple. So what was it? Why don't we just do it as a chi-square independence test? Well, we could, but the advantage of doing it, putting it actually into a regression equation and doing it as a multiple logistic regression is we can see, okay, it looks like females have a better chance of getting in. But what happens if but we want to maybe, if we're really interested in that question, is there sex discrimination or not? We'd have to control for other variables. We'd have to add what's called covariates in our model to control for that, right? I mean, maybe females have a better chance of getting in because they have higher biological science scores. So why don't we control for that? In other words, in a multiple logistic regression model, we can, if we add both of those, females and biological science scores, like last time we saw biological science scores are a good predictor. I mean, they're of getting into medical school. And gender, we also saw that. It wasn't, we have a very small sample size, so we don't know if it would be significant, but certainly it's favoring females, and certainly people who have higher biological science scores get it. So maybe it's just because when we did them separately, they're mixing. We can't tell whether females have a better chance of getting in because it's sex discrimination. Maybe they just have higher biological science scores. If we put them both into the same equation, what we're doing is this coefficient in front of females will tell us for male and female who have the same exact biological science score, is there an advantage to females? And when we look at this, we see, yeah, it's even more. It's higher than it was before. So what's going on there? It's surprising. So that means that if you control for the biological science, that means that women have worse biological science scores. So when you control for them, it shows that there's even a stronger advantage. All right, let's look at this. So the process of going from a simple logistic regression model to a multiple logistic regression model is exactly like what we've done before in regular regression. So this is why it's going to be very easy for you. The concepts are all exactly the same. The only thing that's switched is that now we have logistic regression, but the idea is completely the same. The coefficients in the multiple regression equation are generally different. Why? Because they indicate the change in the outcome controlling for the other variables in the model. That is, assuming the other variables are held fixed. So we're going to combine the two predictor variables that we've done so far. I'm looking back here, like we did. Here's where we did the biological science. So the slope for that was 1.276. And then, now the slope for gender is that. Now when we combine them both, if they were all positively correlated, we'd think they'd be lower in our multiple regression, but they're higher. This one's higher and this one's higher, and that's because there's a negative correlation between gender and biological science score. In other words, women have lower on the average biological science scores, so it means that once you control for that, the advantage for being female is even higher, and now it's significant. All right, so let's look at this. So, so here's our slopes now. And here's our regression equation. It's we have an intercept of negative 17 plus 2.015 times gender plus 1.66 times biological science score. So look at the equation, who has the better chance of getting into med school. So you're looking right here, and females do, because why? Females, because the slope here is positive. The coefficient in front of gender is positive, and females are coded as 1s. Okay, so it means as you go from 0 to 1, right, in the log odds, you have an additive, that's the additive amount that changes, that helps the log odds for females, and then e to that factor, to that slope, is the multiplicative factor that compares the odds. It's the odds ratio, compares the odds of females to males. All right, so what's the odds ratio? Well, that's just what I just said. The odds ratio for gender is going to be e to the 2 point. Okay? It's e to the slope in front of gender. And that's equal to approximately 7.5. So what does that mean? As opposed to before, it was 2.25. It means the 2.25 meant if lumping everything together, disregarding scores and who has better scores, who has, on biological science scores, just females have a higher odds of getting in. We thought that might be because maybe they have higher biological science scores, but it turns out they have lower, so that's why this 7.5 is the odds. I'll write it down. It means that the odds of being accepted to medical school are 7.5 times higher from females than males. For females than they are for males, given that you're comparing two people with the same biological science score. So if you compare two people, one's male and one's female, with the same biological science score, this is the ratio of their odds. And how about for biological science score? That also increased, and that is 1.66. So the odds ratio, this is for gender, and the odds ratio for biological science score is going to be e to the slope for biological science score. And so that's 5.26, whereas previously it was something like 3 point something. We did it. It was e to the 1.276. Right, which is 3 point something. Okay, so, all right, so what does this mean? It means that the odds of being accepted means that the odds of being accepted are what? 5.26 times higher for each, additional point on your biological science as you go 1 unit increase in your biological science score. So for each additional point on the BS exam. Given what? given the same sex. So comparing two males to each other. Okay, so that's the idea. Any questions so far? All right. Does that make sense? So this is an advantage to putting, to adding, I mean, we haven't finished. I mean, if we really wanted to do this, we'd have to add more covariates. What else do you think might matter? Maybe females have a big advantage in interviews or something, or in some other factor, or in their GPA or something. We've just started to do this. But it's the huge advantage of having a model instead of just doing a independence test, a chi-square independence test or a two-sample z-test. When you build a model, you could actually, if what you're interested in here is really, is there some kind of sex discrimination, this would be the way you'd go. Which is, by the way, what we were doing in an honors project. This was what somebody was doing in a James Scholar project, and that's, okay. Now, unfortunately, look at this. This is terrible that somehow this is, even though I'm giving them the same manuscript, this is happening. I don't like this. So this is what? Log of p times 1 minus p. This is exactly what you had on the previous page. It's this. And somehow it just got messed up over here. That's all. So let's just write it down again. So this is the log odds, p over 1 minus p. This is just the log odds. And from the previous page, negative 17 plus 2.015 times gender plus 1.66 times the biological science score. So that's what we're using, this. And we're using it to fill in this table. Wow, are we finishing early? Oh, okay. All right. So what would we do? So here, if for a female, how is this going to change? Well, what's going to happen? The log odds are going to change from what? We're going to put everything in here, but we have to add what? Here, what we're doing, I'm slowing it down a bit. Negative 17, what did I do here? Plus 2.015. Males are coded as 0, so I put a 0 in here. Plus 1.66 times 10. That's how I got that. All right? And then if it was for a female, I'd just stick a 1 in here. So here, the log odds, here's that additive increase of the slope here. We're just going to add that. And what do we get? 1.65. And here, what are we going to do? When we exponentiate, we have e to the minus 0.4 plus 2.015. So there's the multiplicative increase of e to the slope. Okay? Or you could have said e to the 1.65. It's the same thing. And this is equal to e to the 1.65, which is equal to approximately 5.207. So then the probability is what? 5.207 divided by 1. This is probability is odds over 1 plus odds. So it's 6.207, and that's equal to 0.84. So 40% chance versus a 84% chance here of getting in. Now why don't we do a few iClicker questions on this? Okay, so let's just go to the iClicker questions are just asking you to for these two blanks. Actually, for this one, but we already did it, so we'll just do these two. Okay, so let me just. So this is the one we've just did. All right, so let's do this one. So you're comparing it to the in your notebook, just compare it to the top one was e to the negative 0.4. So now you're going up one in the biological science score. So which one of these would it be? The odds would increase by what? E to the what? Okay. Has everybody had a chance to do this? Should I stop it? Okay. All right. And let's see what you chose. Okay, that's good. And yeah. That's the answer. Whoops. That's not the answer. That's the answer for the other one. There's the answer. So you got it right, mostly. So let's do the next one. Whoops, that's not it. That one. Okay, so let's stop this and let's see what you answered. Good, that's right. Okay. All right, so let's go back to the document camera and we can fill that in here. And here you can just put in the appropriate, or you can look at this one, the 0.4, and you can say this one's negative 0.4. You're going up 1, so it will be plus 1.66. And that's what you added here. And then to get this, we just said, I'm just giving you the answers here. I think you know how to do this. And here it would be negative 0.4, because you're going down 1.66. Okay, so now, and your homework is just filling in a chart. Yes? How I get this? Because I'm going down 1, so instead of going, instead of up 1, here. You can see that if you could start from scratch, put a 9 in there instead of a 10. Another way you could do this, if you wanted to do this one, you'd say negative 17 plus gender is 0, right? So you'd say 2.015 times 0, so that's the same as this one. And now you're going to say plus 1.66 times 9 instead of 10. So it's subtracting off a 1.66 compared to that. Okay, any other questions? All right. So now, A female has a biological science score 2 points lower than a male. How do the odds of the female getting to med school compare to the odds of the male getting in? All right, so it's lower. So the odds, let's remember the odds ratio for the gender is equal to what? E to the 2.015. And the odds ratio for the biological science is equal to E to the 1.66. All right, so now comparing the female to the male, she's going to get her odds are going to increase by 2.015 because she's coded as 1 and the males are coded as 0. So this is what she gets for being, she gets this advantage for being female times she's going to have a disadvantage for getting lower, 1 point lower. So she'll have a disadvantage 1.66 for each point lower, right? So we can multiply that times 2 here, or we could just say, if you want me to go step by step, this would be 1 point lower. It's a negative, excuse me, 1 point lower. You divide by 1.6, she goes down a point, times another one, negative 1.66. So that's another point lower. That's the second point. So it's the first point, right? Or you could write it as E to the 2.015 times E to the negative 1.66, but it happened times 2. And that equals, when you add all those up, that minus that minus that, look, that's 2.05 minus what? 3.2, 3.32, right? 160, 3 point, now I'm going to slide, 3.32. Yes, so that's going to be E, a negative. So she loses out more than she gains by being female. So her odds are only going to be 0.27 times as high. You could do it on the computer. You can do it on your calculator. Let's just do it to make sure I didn't make a mistake. So we can say, okay, so we'll say E to the 2.015, right, minus 2 times 1.66. So that's what we get. All right. So the odds of the female are approximately E to the negative 1.305, which is approximately equal to. All right. So what we're doing is, look, the female has an advantage of this in the log odds equation of 2.015. But if she goes down 1 point, only goes down 1 point, she'll still have a higher chance of getting in. But not if she goes down 2 points, because going down 2 points, she goes to, you know, she's still 2.015 is greater than one of those, but it's not greater than 2 of them. So when would she have an exactly equal chance of getting in? When her biological science score is this, when a man has a biological science score somewhere between 1 and 2 times the females. So the odds of a female getting to medical school are the same as the odds of a male getting in when the female has what? A biological science score how much lower? Can you just see it from when those were going to be equal? Like 2.015 is equal to 1.66 times what? It would just be 2.015 divided by 1.66. But here we can do it out here. So their log odds equation, if you don't see that right away, you can just say, okay, their log odds equation for a female is negative 17 plus 2.015, 1 for being female, right? Plus 1.66, and then she has some biological science score. That will be her score. And that has to be equal to the log odds equation for the male, which is negative 17 plus 2.015 times 0 plus 1.66 times his score, biological science for the male. Now these can both cross off, and now we're left with this. So 2.015 is equal to 1.66, the biological science score for the male, and subtract that from both sides to get minus 1.66, the biological science score for the female. So now you can divide both sides by 1.66. This is just what we did in our heads before. And we get the difference between the two scores. We'll get the difference as that. And that is equal to 1.214. So when the male he has to have 1.214 higher than the female to get it exactly equal. All right. When the females is that much smaller. So that's the advantage so far, but that doesn't mean that's not, we should add other covariates in, like maybe the females have a higher GPA. So we should add that in if you really wanted to get at whether there's some strong advantage to being a female, if there is sex discrimination. You see, I started off with this problem thinking males had an advantage of getting in, so it was quite a surprise. And that's the nice thing about statistics. You can be surprised and it removes your bias. I mean, I figured it would be males would have an advantage, and so far it looks like that's not true. So that was, that's a good thing about statistics, is it really helps you look at things more objectively than you ordinarily would. So that was helpful to me, but I haven't really explored it fully yet. And this is just a small data set, but I think it is an interesting thing to look at. All right, now, let's see. You know what I think I'm going to do? Because I don't want to rush through this too much and give you cognitive overload. And this one, next chapter, is kind of hard to understand. So why don't you just stay and finish your homework up if you want now, and I can help you with it, or it's posted, or else you can just leave now.